Great. Hi, everyone. I'm sorry for the delay, but let's get started with visual servoing. Cool. So yesterday, we talked all about the object detection, and today we're going to get into the actual control problem. So the title of today's lecture is the control systems part of visual servoing. And I'm going to play a few videos for you. So the video on the left is supposed to be parking at a cone. So it's going to take a little while. This is a video from students in the class this past year. And again, it's just using the onboard camera to determine how the car should drive, and even when the car should stop. So you guys are going to be expected to do something like this today with the same type of cones and the exact same type of cars. And you'll even have a very similar lecture on how to do visual servoing. And then tomorrow you're going to extend your project to do line following. And in this one, we're going to ask you to go as fast as possible, although while using your safety controller and within safety guidelines. But you will get to go a little bit faster than this. This one was the TA car implementation, the very first one we had. And then we kind of improved upon that. So again, the idea of visual servoing is the control of the car, and it's computed only from the video camera. And we're going to talk about how you can do that. So let me just make sure my things. We're going to go a little bit over the control systems review. And here we're going to really review the things we talked about last week, including the feed forward versus feedback control. We're also going to talk about PID control, just kind of as a refresher. And then we're going to bring those topics into the context of visual servoing. We're going to talk about what is the state of the system and what is the error signal. What does that mean with respect to the actual actuator commands? And then we're going to talk about the parking. When do you decide to stop? And also, how do we do the line following? So this is an overview of a control system. Hopefully it looks a little bit familiar to you. We have some black box controller that we don't really know what it is. And we have an input to the controller, which can be what the desired aspect is. So this could be something like the cruise control. We want our car to drive at 60 miles per hour. And somehow this controller will ideally do something to make sure that the car is driving at 60 miles per hour. The first type of control we talked about was feed-forward control. We also called this open-loop control. And that is when you pass the command you want just directly to the motor and hope it goes. So what is an example of feed-forward control in the context of visual servoing? So suppose I wanted my car to park, and I just had it stop and look at the cone. And then it just estimated, okay, I should probably drive forward for maybe 3 seconds, and then turn at maybe negative 15 degrees for 2 seconds. And then I just had it drive and do that. That would be an example of feed-forward control. During the RSS class, we had students drive their car in a circle along a yellow line that was on the ground. And we asked them to try to make their car drive in the circle as best as possible without using any of the visual servoing. And they saw very quickly the car would diverge from the circle. And it was really surprising, and I think it was very useful for the students to go through this activity, because even though you're sending these commands, they don't always work. And it's not always clear, how much will your car directly follow your feed-forward commands, what you expect for it to happen. And I encourage you, if you guys get done with the labs early, try to set up a system where you just do, I'm going to calibrate and think about how I'm going to control a car, and I'm just going to send the commands and see how well it works versus how well it works when you're doing visual servoing. And I think you'll be surprised at how poorly this can work in a real system. It might work in Gazebo, though. So what was the closed loop control? What makes this different? I'm going to ask someone in the audience. So, Omri, you want to be on the spot here?
A closed loop is different from an open loop because the output is recorded and fed back into the controller, so that as opposed to just blindly executing scripted program, it actually changes its behavior and reacts to its environment in real time.
All right, thank you. I don't know if you guys could all hear Omri, but he gave the excellent answer, which said the closed loop system looks at the output signal. So before we had, the big controller, just a big black box, and it just went straight forward, Here, we look at what is our output signal, and we drive it back into the system and use that to, as an input to our controller. So the example for the cruise control is actually looking at what is your current speed and then deciding should you, increase the car speed or decrease the car speed to be at, say, 60 miles per hour. So I just want to review some of the variables of the control system before we get further into the problem. Traditionally, the input to the controller or this whole module is called a reference signal. So this could be 60 miles per hour or whatever you want the desired state of the car to be at. So we can describe that as R of t, where t is time. The error signal, well, why don't we jump to the end? So at the end of the thing, there is that output signal. This is the state of the car. So again, a lot of times these variables can be named different things. But here we're going to call it y of t. And I'm going to try to stay consistent with this variable naming throughout the presentation. So the actual state of the car is y of t. And here's the desired state of the car, r of t, reference signal. We're going to look at what is the current state of the car and what is our desired state of the car. And we're going to subtract the two. This is going to give us our error signal. This is, is the car going 5 miles per hour too fast or, 5 miles per hour too slow. So the error signal is what gets fed into the controller. The controller, based off of this error, is going to decide, what should the actuator commands be. So that's going to be the control signal, u of t. And then traditionally, we call the actual system that we're going to actuate a plant. In our case, that's going to be the race car. In proportional control, the way we do this one is, again, we look at the output. And the controller is a very specific controller. The controller is going to look directly at this error signal and just multiply it by a gain, and that's going to be the control input. So I think, do you guys remember implementing this one? Good. So in the proportional controller, does it work? And one of the ways we can ask, does it work? One of the things we could say is, does the output y of t, so that's the state of the car, does the state of the car ever settle? Yes or no? No. So sometimes, it depends on the system. Sometimes a proportional controller can be entirely sufficient. But sometimes the output y of t does not settle. What can it do instead? So, any, okay, yep. You have an answer from the audience?
Can oscillate on either side.
It can oscillate on either side. And there can also be a steady state error. And that means, we could, the example we had last week, which was the cruise control, suppose our car is at the exact location we want it to be at, the exact speed we want. And so the error would be 0. And we multiply that by a gain. So a gain times 0 is still 0. And we send that to the car actuator. That's going to make the car speed slow down because you're not sending anything to the motor. So sometimes you still need to actually apply some throttle to make a system keep going. And in the PID controller, we can start to try to improve these things. So we have the steady state error, and we also have the oscillations that we can try to improve. So as we were saying, we can add this KD term. So this is what you're talking about, the oscillations. This is probably what's going to be most important for your application of visual servoing, is make sure we add some sort of damping term to try to make it converge to our desired reference point. Don't overshoot. And so the PID controller is this combination of all of these different error terms. And last week we had some questions on, well, how do we compute them? So I wanted to put up some formulas up here, and you guys are welcome to use them. We're not going to get into them too much, but we were talking about how we could estimate the derivative. So the derivative of a function is defined here. So suppose we have some value function that's f of x, and we look at some small deviation. This is just the derivative. I'm not going to go into it, actually. We'll learn it in calculus. But here, we're going to show how we can estimate it from 2 points. And again, this isn't to really go too deeply into here, but I did have a lot of questions on what's the formula, so I just wanted to provide them here. So this is called the finite difference method. You can read about it a lot more online. And the big thing to point out for it is that it works really well when the deviation between the 2 points that you're using is small. And then also for integration, something that you can use is called the trapezoid rule, which the integral is supposed to be the area under the curve, and instead you're just going to estimate it using a trapezoid. So again, I know I'm throwing formulas at you, but we had a lot of questions, so I just want to make sure you know what you could use if you wanted to implement your PID controller. And you guys will have all the lecture slides online, so you can look back at them. So now we're going to get back to the image-based visual servoing. We're going to try to tie this, the control stuff we were just talking about, the P controller, the PID control, to our original problem, the line following or parking at a cone. So we have the canonical control problem, the input to the controller, and we have an output of the controller. For our particular application, we will have the output of the controller be the actuator commands. So this is going to be an Ackermann signal, so the steering angle and the velocity we want the car to drive at. But the error signal is going to be different than, say, the wall following thing we did last week. And we are doing image-based visual servoing, so that means the error signal is going to be defined based on features of the image. And this is different from position-based visual servoing, which we're not going to get into, which does some sort of real state estimation. in terms of like what are the actual physical units of the cone with respect to the car. So we're not getting quite into that. Instead, what we're going to do is want the video of the car, the video input, to look like this signal. So it's a little bit different way of thinking about the problem. But we can still define it as a traditional control problem, and here we'll go into how to do that. So here we have the feedback control loop, and we're talking about the different variable names. So we have the reference signal, this is the input. We desire the cone to be at the center of the image, so this is RT, our desired input. The error signal is going to be a distance metric. You know, how far is the cone from the center? So how are people's object detectors going? We were working on them yesterday. All right, I'm seeing good signs. So hopefully you are ready to look at this problem. How do we compute the error signal this morning? We're going to do a controller. So in this example, say we just use the proportional control. I recommend using that first, making sure you have the system working. Think about improving the control later. And then you have the Ackermann steering commands. So what is the turning angle and what is the speed we want it to do? And the plant is going to be our race car. And the output's going to be the current state of the car. And we're going to estimate that with our video image. So I'm going to show you how I would solve the problem. You can go through the steps of trying to define the control problem and modify it as you and your team want. But I'll just show you how I would do this. So the first thing I would do is define a reference frame. I'm going to define a coordinate system for this image. And in particular, I'm going to say the width of the image is 1, and the center of the image is 0. And I think it'll come to you why I'm doing that later. Just, all right, we'll see why she's doing that. But again, I really hope you guys go through the steps of thinking about the problem and defining the coordinate system, defining all the steps afterwards. So here I am defining the coordinate system, and I'm going to say the state of the car is at 0 if the cone is directly in front of it. And if the cone is to the right of it, so I had my hand out like this. If it's to the right of it, then if you're thinking about the right-hand rule, that's in the negative direction. If it's to the left of it, it's in the positive direction. And I also said it's going to be 1 at the bottom. You guys can do this how you want, but this is how I define my system. And I am going to work from here on developing what y of t is. So y of t is going to be where is the actual cone within this coordinate frame I just defined. So the rightmost side, if I detect the cone right here, on this side, it's going to be -0.5. And if I detect a cone all the way on the left side, it's going to be +0.5. So the very first step that I did was write the coordinate frame and then define what is my state. So now we can think about the next step of what is the error signal. So this is that first part of the control plant system that we showed earlier for a feedback loop. And this circle right here is a summation. In control, we have these block diagrams, and they have different components. And later on, I hope you guys will take a control class and get familiar with all of them. Well, this signal means sum, and in here we can see what signs are. So we're going to add R of t and subtract y of t, which came from over here. And this is going to give us our error signal. And since we want the cone at the center, we're going to say R of t is equal to 0, which means our error signal is then the opposite sign of y of t. So here's a very similar picture of what the error signal looks like for the cone. So if the cone is in the center, it's equal to 0. But if the cone's to the right, it's equal to 0.5, and all the way to the left is equal to negative 0.5. So any questions about the error signal? I want to break for questions. Yeah, first one.
Why is 0.5, negative 0.5 on the left? Because in the previous slide, it wasn't negative 0.5 on the right.
Yes, it was. So I tried to go slowly through that, but I probably went a little too fast. I defined the state of the system for y of t, so that was where is the actual state of the cone. But now I'm looking at what is the error signal. So the error signal comes from over here, which is defined by R of t minus y of t. And since R of t was 0, it just gets the sign flipped. But I probably could have kept the second half of the system so you could see y of t coming back through the feedback loop. Yeah?
Sorry, so y of t is the position at the bottom, so like if it's all the way at the left, it'd be, y would be negative 0.5, and if it's all the way at the, okay. Just want to make sure.
Yeah. I'm trying to go through the steps a little bit slowly. Before last time I presented this, I jumped straight to the error signal, but I wanted to show you why the error signal I defined this way. And later on, when you guys are in a team, you're going to go through the steps of defining the coordinate frame, defining what your reference input is, defining the error signal. So I want you to know the steps of what's going on. And that's more important, I would say, than what's the actual specifics for this particular application. So I'm really excited that you guys are going to be your own designers. You guys are going to be your own engineers. You're going to decide what is the control problem and how you want to fix it. So suppose we have defined our error signal this way, and now we have this picture over here that defines, what is going to be the error signal when we detect the cone at the left side versus the right side. If we're using the proportional controller example, that means the command is going to be a gain times E of t. So an example of this is if the car is to the right of the cone, the steering angle should be positive. And that is how I wanted it to be, where I wanted to be able to think about this problem in terms of angles, so that's why I had that right-hand rule at the very beginning. So if the car is to the right, you want it to turn to the left. And if you're careful here, the signs will work out. If you're not careful, you'll have your car going in the opposite direction, and usually it's a sign change. It's easy to fix, but you should know where it's coming from. And just think about it. If your sign is off here, you're going to try to drive in a way that will grow your error. So rather than oscillating back and forth, you're just going to diverge. So you guys will see it very quickly if you have a sign error here. So the method I was just talking about is just about how do we drive the car to the right or to the left. It doesn't really say anything about forward and backward velocity. So in this control problem, I set it up as two separate control problems. I actually said I'm going to control the steering completely independent from how fast the car is going. Now, that may or may not be the best way to approach this problem, but by decoupling the two, it really helps in terms of making sure the steering part works well, and then making sure the forward and backward parts works well. And what I'm excited about here is your team will get to decide, how am I going to make sure it parks? So in this case, we're not using the safety controller to say park at the cone. We want you to actually use the video image to say park at the cone. So an example of doing that is using what is the height of the cone, or maybe what is the area of the cone in the image frame as your control signal, as your state value. However you want to do it, your team is the designer. Your team gets to go through the process of defining the control problem. And again, if you do this, if you disable your safety controller, make sure your car is driving at a very slow speed, and have someone directly behind the car at all times. And do not drive the car by the stairs. So for this application alone, we are going to let you develop and drive your car without the safety controller, but this is a very specific instance, and do not get used to it. We want you to drive with the safety controller at all times, except for when you're trying to park by the video camera data alone. Okay? So I'm going to show a simple addition you can do for line following. So in my problem, since I decoupled the whole idea of steering and driving forward and backwards, I can just directly use the same code, almost, for the line following approach. So here's this fun little video of our car driving over a mountain. It's a pretty big mountain, right? How many people thought of one of those commercials with the truck driving over a huge mountain range? Or was that just me? Might have just been me. So for this problem, right here, the actual code we did was very simple. We used the exact same parking code, except we didn't tell it to stop. Now, that would almost work, except, it depends how you're computing, where's the orange part. Suppose I was just taking the average of the contour I detect, I would find it right in the middle here. So I'd want the car to be over here. And instead I wanted the car to stay on the line. So what I did was chop the first, chop the top half of the image off. So then, as the car was driving, it was always just trying to visual servo, but for something directly in front of it. Now again, this might not have been the fastest way of approaching line following, but it was exciting to see how I could be very modular in my development. I could decouple the system into the steering component and the driving forward component. Trevor wrote a really fun lab assignment that's going to push you to think of other ways of doing this problem where you don't actually think about the two independently. You can think about them together. How do you do this so you can go a little bit faster? Because in this problem right here, the reason our car is going slow is because it always has to visual servo to right directly in front of it, and it's not really thinking about going ahead. So for this problem, you probably want to think of wanting to control more of a trajectory of the car rather than a single point. But does it make sense why we want to remove the top half. So this could just be based off of how you did your object detector. So for mine, I segmented the yellow and took the average of the contour as my state. And that's why the error signal was kind of off. You could be doing your object detection a little bit differently. So I hope during this lecture you're thinking about different ways you could approach this problem to make a line follower that's a little bit faster because you want to be competitive on Friday. But if you want to try something that should work, this should be a good start. So I'm going to wrap up the visual servoing lecture with, again, kind of going over this kind of system for solving a control problem. And it starts with defining a coordinate system. So whenever you have a problem, it doesn't always make sense what the problem is unless you define it with respect to something. So that was, for me, saying what is going to be the state axis. For you, when you guys are doing maybe the forward backwards, you can try defining your coordinate frame there. You should define what your state variables are. So what is the state of the system? How are you going to estimate the state of the system from the sensor data if it's not provided directly? So I kind of mentioned how I took the average of the contour, I segmented out. But again, you guys could choose something different, like if you're doing the parking problem, what's the height of the cone in the image? Things like that. It's all up to you. And then also, what is the reference value? So I wanted my cone to be at 0. Maybe I could have just defined the coordinate frame differently, and then the reference value would also be different. So you can see how, unless you define the coordinate system, it doesn't make sense what state variables or reference values are. And then once you do the first 3 steps, computing the error signal should come directly from it. It should be this sum. You should be able to actually not do very much for step 4. But here, you should definitely make sure you have a value that makes sense. So for every step, you can always debug a little bit, try to visualize what's going on. And then I recommend implementing a simple proportional controller just to make sure the whole platform's working. But then after that, try to improve the control with integral and derivative components. So make it maybe a PID controller, whatever you want to do. Or, take some more control classes and do something a little bit more fancy. And yeah, I think these steps will help you when you approach a new control problem. Okay. You had a question, or? All right. So, I think. All right. This is the end of the visual servoing control part. I just want to make sure I cover any questions on trying to get our cars to park. Yeah.
How did you define your axis to have a width of 1?
So the question was, why did I want my axis to have a width of 1? One of the things you'll notice is if you use the direct pixel values of your image, it could be something like a width of 1048 or some large value. But if you want to go and use it with a different camera, the width of it is going to be different. And so for me, I was actually developing a lot of my visual servoing code on 2 platforms with 2 very different cameras. And they had 2 very different outputs. And in fact, if you modify your Z resolution, you're going to have a different image output as well. So I wanted a simple framework that would kind of put the 2 images, no matter what the original pixel values or size was, in the same, just normalize things. So that was why I chose 1. but it doesn't have to be that way. So again, the first step of your control system is, defining, what's the coordinate system. You have so much flexibility there, so, I'm excited to see what you think about doing. But for me, because I was designing for multiple platforms, I wanted a way to make sure everything was consistent. Does that answer your question?
And 1 was just an easy number to get to?
1's a fantastic number. I would have chosen 0, but that would have not worked. All right, another question up there.
What's the maximum steering wheel then? Is it like 0.3 or is it 0.34?
Trevor, are you out there? What's the maximum steering angle? I think it depends on your car, but yeah. But each car can have some variability, so you could test your car on your own. So I know we definitely had some cars that, although the software says 0.34, the actual physical system can't go quite that far, or maybe it can go a little bit farther. So you can test it out on your own. One of the things I guess I didn't mention was when you're starting this parking, the cone is going to be in the image frame. So you're going to be able to see it when you start, so you will not have to make a super sharp turn. Okay. And I heard there were questions about OpenCV. I'll answer, I guess, 2 of them ahead of time and take a few more if I have them at the end. So I think Andrew mentioned there was a question about how to use text. So how do you label your pictures? And so I have the code up here, and I try to comment it a bit. You guys can, again, use the slides as a reference. Sometimes it's tricky to really figure out from the OpenCV API how to actually write the function, because they have a really weird array notation for some of the inputs. So to put text onto the screen or your image, you have to first define what the font is. OpenCV has a few different fonts that you can use. So here's just a normal one that I found, kind of a boring looking one. I chose the color to be black. The font scale, so that's like how large do we want the font to be, 1. There's a few different types of lines you can have. So I wanted just like a solid connected line for drawing the letters out. So that's what the line type means. And then the text. The text does not work with things like new lines. So it's, if you want something to like put a lot of, glorious text, probably OpenCV is going to be a hard thing to get that all for you. And then you have some point. A lot of OpenCV problems can happen if you don't use integers here. So the coordinates of the pixel that you want the text to be centered out. Okay. And then the function for just writing the text is CV2 put text. Okay. And the other question I had was on a bounding box. So the previous code I showed you should work. It is actual code from my software. This one is almost actual code from my software, except I didn't put in all the inputs for fine contours because that seems to be like 20 lines long. But fine contours will return 3 values, say an image, contours, and something about the hierarchy of all the contours. The hierarchy thing, it depends on the input to find contours. You could say whether or not you even want that. So usually when I do this, I ignore the image. That's just like a copy of the thresholded image. And hierarchy, I ignore that too. And I just look at what are the contours. And then suppose I want to draw a black bounding box around a contour. I'm going to do the same thing. I'm going to define the color as black. I'm going to make the scale be 1. And then contours is a list of different contours. So for each contour in contours, I'm going to get the bounding box of the contour calling this OpenCV function. This is going to return 4 variables, so it's going to return x and y for, I think, the upper left corner of the box, and then what is the width and height. So then, to draw an actual rectangle, I will use the CV2 rectangle function, where here's my image. I want the box to start at x, y, and the right-hand side to be x plus w and y plus h. So that's going to define the corners, and it's going to draw a box there. And then I tell it what's the color in the scale. So this code should almost run completely, except find contours doesn't have the full input. So the syntax is consistent, though. So extra tips when you're doing the visual servoing. Use ROS-bags to record video streams. Please use ROS-bags to record video streams. It's going to make your life a lot easier to have like a test input. Try to run your vision detection software on it. Make sure the output is working. Once you have that part working, try to make sure your control is actually actuating the wheel. So you can really go through and step through all the parts of your system, make sure each part is working before you get to driving the car. Because again, we are kind of disabling the safety controller for a very brief moment. So we definitely want you to be as safe as possible. And debugging using ROS-bag is really going to help you do that. If you haven't already, when you're launching the Z camera, look at using the Z wrapper to decrease the quality of the images. In the lab yesterday, we asked you to look at RQT image view and see how is the playback when you have different resolution values. And so if you went through that process, you probably saw a lot more lag with the full quality Z camera, from the Z camera. So if you want to have very fast performance in your vision code, you probably need to decrease the resolution a bit. And then I was going to I encourage using actual pixel data for setting HSV thresholds. So in that case, I know I had some students open up GIMP and figure out what are the coordinates of the cone to figure out what is the actual RGB values to get the HSV values out. So having some schema like that is going to really be beneficial. I was going to have a demo to show you how you can do that, but my computer wasn't displaying, so I'm in Windows right now. So when we get to lab, I can start off with the little demo to show how to access pixel values if you guys are interested. But again, if you're looking for HSV thresholds and Googling them up online, they don't usually work very well. It usually works best if you try to actually get them from the image you're working with. Okay, so that was the visual serving lecture and a few more things about OpenCV. And I think if there are any extra questions, or are we ready to start lab? Lab, all right. Thanks, everyone.